Hello, Calculus. We are working on section 4.5. This would be the first day that we introduce the U substitution technique for finding integrals. And this technique will become very handy for dealing with functions that are composite functions. So what do I mean by a composite function? Well, you understand the notion of a composite function. It's like an outer function with an inner function inside. So I could say like I have x squared plus 5 raised to the 7th. There are two functions here. My outer function would be the 7th power. So I could say I have some function, maybe u to the 7th. And then my inner function would be the x squared plus 5. Oh, you know what would even be better? To say that I have f of x, my outer function being an x to the 7th, and then my inner function was g of x equals x squared. And when I put them together, I insert g of x into f of x, and it builds this idea, or it builds what we call a composite function. So here's the name of the game. Finding the integral of composite functions can be a little bit more difficult than just finding the integral of, say, x squared plus 5. We've been doing that now using the power rule. We knew that this came out to be x cubed over 3 plus 5x plus a constant c. That was pretty easy. We got through that stuff. Now what we're going to do is increase the difficulty on this and maybe put a power out front here, or raise that function to a power. Now that just complicated it. If we could, I would expand this, and think of this as x squared plus 5 times x squared plus 5, and so on 7 times, and then create one nice big long power, a polynomial of each term, but I'd have to multiply all this stuff, and holy cow, that would take forever. So there is a much more efficient way to deal with composite functions. So that's our U substitution. So get the idea flowing here. When I take a derivative of a composite function, recall how we do this. We work with the 9. We work with that outer function first. So the 9th power, the 9 comes down. I leave my inside function alone, and then I raise it to the 8th power because I reduced 9 down to 8 in the process of taking the derivative. Okay, that dealt with the outer function. Next step is I got to work with the inner function, which would give me a 4x from the inner function. That's the derivative, isn't it? Well, what happens if I integrate this derivative? And I would integrate, let's call this 36x times 2x squared plus 3 raised to the 8th dx. If I find the antiderivative of this, it will bring me back out to that original y that I started with before I took my derivative, right? So by taking the derivative, I had this, and then I said, okay, let's take the antiderivative of the derivative, and that's going to bring me out to my original function. All right, just a little bit of the game plan of what we're after. So hand you this function. It's 4x times a function raised to the 7th power dx. The first thing I'm going to ask you to do is look for the expression, the inner expression that has the higher degree or the higher power. And I'm comparing like my x squared, and here's just an x. This is great because I have x squared and then a power of 1. They have a difference of just 1 power, and that's perfect. So I'm going to select the expression with the higher degree, which was my 2x squared plus 3. That I'm going to set up to be my u. And then I'm going to go over to the side here, and I'm just going to do a little bit of calculating. So if I let u be that, and I take its derivative, so the derivative of the left side, letting x be my independent variable, so I'm going to take it with respect to x, I'd have du dx is equal to, now take the derivative of the right side, 4x, and the derivative of x would be dx, so I don't need to write that, and the derivative of 3 would be 0, so far so good. And I bring it back over. Now I'm going to come back over to the right side, or the left side here, and I notice that I said I'm going to let this piece be my u. what I'm trying to do is write everything now in terms of u and then du so that I can integrate it. I want everything to switch over. So far I figured out that I've got this much replaced and I'm replacing it with u. What remains is a 4x dx. So I'm going to travel over here to the right and kind of analyze what I have over here. I have that 4x, right? Perfect. But it needs to be multiplied by a dx. Oh, I can do that because I can simply multiply both sides by dx. And now this will cancel or reduce to 1. And I get du is equal to 4x times dx. Perfect. Because I'm going to replace 4x times dx with du. So what have I done? I've taken this complicated integral and created a very nice integral out of it in terms of a different variable, but that's fine. So now that I can actually integrate this, I'm going to take this integral of u to the 7th du and call it u to the 8th divided by 8 plus c, right? We add a power, divide by the new power when we find the antiderivative. So I'm no longer integrating. I've got my antiderivative. And the final step is to sub back with the original expression. So I'm going to take this integral that we started with. Let's go back and rewrite this. I had 4x times 2x squared plus 3 raised to the 7th dx. And I figured out that it is something raised to the 8th power divided by 8 plus c. Well, let's replace this u back with what u was originally representing. So 2x squared plus 3. And there's our answer. If you don't like the 8 underneath, we could call it a 1/8 times 2x squared plus 3, get parentheses, raised to the 8th plus c. Maybe you like that picture better. All right, I'm going to skip over problem 2 just to save some time because I have a meeting I have to get to in about 20 minutes. Let's go to problem 3 because it's just a slight bit harder than that problem 1. But some of the same techniques you're going to see. Okay, so I'm looking for a term of x with the highest power, and I see an x to the 4th versus an x to the 3. The great thing about each of these is that they are different by 1 degree. So that when I take the derivative of something raised to the 4th, it becomes a power of 3, doesn't it? Because I reduce the power by 1 when I take a derivative. This, I think, is an excellent choice for my u. I'm going to let that be u. So, and I've done these a bit, you guys, so I know exactly what I'm looking for. For others, it might be a little bit of a guess and check game, and that's fine. In math, we don't always select the perfect thing to start us off. That's where you have to persevere and try something different if the first thing you went through doesn't work. So I'm going to go over to the right here and set up my u sub. You saw me working it out. And I said, let u equal this. Let's try and take the derivative. So du with respect to x, so dx, is equal to 20x to the 3rd and then dx, which I don't need to write, plus that 0, which I don't need to write. Coming back over to the side here, I've got my integral. I'm letting u equal the 5x to the 4th plus 2. That'll be raised to the 4th. So I've taken care of this stuff. What still remains that I have to account for is 80x cubed times dx. So I'm over here on the right and I notice, what do I have? I've got 20x cubed and not a dx. But we can cure the dx real easy, can't we? Let's multiply up by dx and that'll give us 20x cubed dx. So I'm a little closer. Got the dx accounted for. I see an x cubed, but I need 80 of them, not 20 of them. Well, how can I solve that? Let's multiply both sides by 4. Would that not be fair in math to, if I have an equation, multiply both sides by the same thing? Exactly, we can do that. So I get 80x cubed dx. And now my substitution will be complete because this stuff is going to be represented by 4, I didn't write d, du. So here's my integral, u to the 4th du. I want to integrate that expression, and that'll be a u to the 5th divided by 5, or you say multiply by 1/5. And then don't forget your constant that could be existing. And the final step, I can say the integral of u to the 4th du is equal to 1/5 u. Instead of u, I go over to my chart. This is what's nice about creating a little u sub box, is I can access it and see exactly what my u was equal to. 5x to the 4th plus 2, and then plus c. And there's your problem. You can check your work on these. That's the beautiful thing. If I took a derivative, if I took the derivative of this, of course the 5 is going to come down. Well, there it gets canceled by 1/5. It changes to a 4th power. This is gone. And then I'd have the chain rule. I'd multiply by 20x to the 3rd. And does this not exactly look like, oh shoot, oh, somewhere I lost my 4, didn't I? Oh, you guys, I pooped this. The 4, when I put du here, I needed to get a 4 with it, didn't I? I'd have 4 du. Good thing I checked my work. This 4 can come out front. And so when I integrated this, then I would have had that 4 multiplier. So this becomes 4/5. This becomes 4/5. And now the 5, when I took my derivative, cancels the 5. 4 times 20 equals 80x cubed. 5x to the 4th plus 2 raised to the 4th power. And I'm back to where I started. Wow, I'm glad I caught that. Because that's the thing that was just a little bit more difficult on this problem. The fact that we had to do a little bit of work to match up with the 20x cubed didn't match perfectly, so we multiplied by a 4 and got our 80x cubed. And my critical mistake when I started rewriting this was replaced by a 4du, which I bring down into here then. And now the 4 can come up front, u to the 4th du, which becomes a 4 times u to the 5th divided by 5 plus c. And then we get 4/5. Replace our u with 5x to the 4th plus 2, and then plus our constant. Awesome. Okay, I'm going to skip over 4 because it's very similar to number 3. And let's go to, I'm going to go to 6 because it's the more difficult one. Number 6. So I'm looking for powers. Well, these actually are very similar, aren't they? I've got an e to the 3x and an e to the 3x in both cases. So which should I choose for u? Always look for the more complicated. And it's more of a composite function here because I have an inner function and an outer function of this 3rd power. So I'm going to allow this to be my u. So I'm going to come over and do my little u sub lines over here just for my own reference. This u sub box just becomes a very nice organizational tool for us. And it allows other people to see your work and your thinking. Okay, so I notice what remains because I'm going to be able to take care of all of this with the u to the 3rd. So what I have to match up to are these 2 items, the 9e to the x, e to the 3x times dx. So let's go over to our u sub box and just do our work. So I get du dx is equal to e to the 3x. Now the derivative of the upper function will be a 3 because that's a chain rule, and then I'd have minus 0. All right, let's multiply up by dx. So du equals 3 e to the 3x dx. It's comparison time. So I'm going to go back over and look up here and see what I had to match to. Well, I noticed that I don't have a 3, rather I have a 9. So can I turn my 3 over here into a 9? Certainly, all I have to do is multiply each side by a 3, correct? And I get 3 du is equal to 9 e to the 3x dx. All right, take it back over to the left here, and let's do replacements. I have so much written here. I'm just going to clean up my board. This I'm replacing with u, so I get a u to the third. These two items are multiplied, and they match up with this down here. So that becomes my, I'm not going to mess it up this time, that's going to become my 3 du. But since I have a multiplier, I can bring it out front by properties of integrals. And now super easy integrating, wouldn't you agree? Oops, put a 4 down there, not a u. And then we simply replace. I'm going to call this 3/4 right away, where I'm bringing this 4, which is really 1/4, out in front, so that it becomes 3/4 now. And then something raised to the fourth. What was u? Well, now my eyes travel back up here. It says u is equal to e to the 3x minus 3 plus a constant. All right, so the homework is a worksheet that has problems 1 through 10, and that's not it. That's going to start our next day. So you can maybe print that from Schoology. I'll post it up to Schoology so you can get access to it. Awesome. Have a great day.